Swayam Prabha. Digital India. Educated India.
Good morning and welcome to this the lecture number 39 of the course Stochastic Hydrology. In the last lecture we essentially discussed about data issues, specifically touching upon the data consistency checks, and in the previous lecture we had talked about the double mask curve for data consistency, and in the last lecture we also covered the concept of specific flow and how we use this concept to examine the consistency of data, which is this particular method is especially useful when we are talking about large catchments where a number of gauges are recording the flows, specifically the flows, and then we would like to examine whether the flows in fact are consistent with each other as recorded from various gauges. And we took up the case study of the Narmada basin and then examined at various sub basins how the specific flows compare with each other. Then I also discussed in the last lecture the data representation through box plots. Box plots essentially will provide a good representation for the uncertainties starting with including the range. It shows the range between minimum flow and maximum flow. It also shows the median, it shows the 25th percentile, 75th percentile, and sometimes we also put the mean. Now, these box plots are useful especially when we are comparing different time series or the variability of a particular time series across time, across different time windows. Let us say that you have a long time series of 100 years of flows. You would like to examine how the variability was in the first 20 years as compared to the next 20 years, as compared to the next 20 years, and so on. So, these box plots are handy tools for examining such variability in the data. Then we also discussed in the previous lecture how we normalize the flow data. When we have the gauge data which are contributed essentially the flows at a particular gauge are essentially contributed from controlled flows upstream of that particular gauge location, which means you may have a reservoir or you may have some other control structure through which the flows are coming, and then you are recording the controlled flows at this particular location. And for all analysis I have been emphasizing that you need naturalized flows or normalized flow, which means you have to take out the effect of the anthropogenic interventions in terms of the reservoirs or in terms of any other controls, let us say lift irrigation schemes and so on. You may have several such anthropogenic interventions, structural interventions that have taken place in the stream, and therefore, the recorded data will have signals of the controlled flows, and these signals have to be removed, and then you convert the flows as natural flows, naturalized flows, and then do your analysis using the techniques that we have covered in this course on the naturalized flows. So, we have covered how to convert the flow data at a particular location into normalized flow data or naturalized flow data. That essentially completes the portion that is set out for this particular course. So, in today's lecture what I will do is this is a special lecture as the last lecture before we summarize. I will cover a recent application of most of the techniques that we have covered in this course, and this topic is timely because in hydrologic research most of the research that is going on is in this area. So, I will just give a broad flavor of how we use the techniques that we have covered in this course to in this particular area, and this area is the climate change impacts on hydrology. So, this is a special lecture where I will just give a broad flavor. I will not go into too much of details of how we do the modeling and so on, but given that we have gone through 38 lectures so far, we will know all the methodologies that I will be discussing. So, I will not go into the details of what kind of numbers we get out of the methodologies and so on. So, we will just go through the broad idea of the concepts that are involved and the modeling aspects that we do using the statistical techniques that we have learned, stochastic techniques that we have learned. So, this lecture is on hydrologic impacts of climate change and especially on the quantification of uncertainties. And I have taken these slides from my PhD student's thesis presentation. His name is Subimal Ghosh. He is already a faculty member at IIT Bombay after completing his PhD from IIT Bangalore. So, the slides that follow are essentially taken from his presentation with permission. As I mentioned in the previous lecture, the issue of climate change impacts on hydrology is the one that deals with relating the long term changes that are happening on the climate with the changes that are likely to happen in hydrology. As I mentioned in the last class, the global average temperatures are known to be changing, known to be increasing in fact, as a result of which the sea levels are rising and the precipitation patterns across the globe are varying, are changing. All of these three prominent signals of climate change have direct implications on hydrology. They will affect the precipitation patterns, regional precipitation patterns, as a result of which the hydrologic extremes of floods and droughts are likely to change, the magnitudes are likely to change, magnitudes of the floods, the frequency of the floods and vulnerability of various regions due to floods, all of these are likely to be affected. The water availability in a river basin is likely to be affected. The evapotranspirative demands of the crops are likely to be affected, and in countries like India, where primarily the water resources systems are operated for irrigation, irrigated agriculture, these will have direct implications, and the rise in sea levels will have implications on the coastal inundation, coastal flooding, as well as on the salinity ingress into the groundwater. So, the climate change impacts need to be studied at regional scales, taking into account the projections provided by what are called as the general circulation models or the global climate models. So, in this lecture we will see how we do that and also how we address the uncertainties associated with our projections, because standing at this point in time we need to assess what is likely to happen to, let us say, the water availability in a particular river basin over the next 20 years, 30 years, 40 years and perhaps one full century, because our water resource systems are designed to operate, designed to serve for next about 100 years, and therefore, we should know how these systems are likely to perform in the face of climate change over the next so many years. So, what we do is that we pick up the simulations of climate variables as provided by the general circulation models. Now, the general circulation models, as I mentioned in the previous class, are essentially models of climate, and these are driven now by the greenhouse gas emissions and typically the CO2 levels, CO2 emissions into the atmosphere. And corresponding to the various levels of CO2 emissions that are likely to happen in the future, we have what are called as a scenarios, that is emission scenarios. For example, one of the emission scenario can be double CO2. That means, in a particular time frame the CO2 levels will be doubled. Like this we have several scenarios. These are given by IPCC, the Intergovernmental Panel on Climate Change, IPCC, and for these scenarios the climate models provide us the projections of climate variables, several climate variables. For example, what is likely to happen to temperature, what is likely to happen to relative humidity, what is likely to happen to pressure levels at let us say geopotential height, that is gravity adjusted pressure levels and so on, and what is likely to happen to sea surface temperatures, mean sea level pressure and so on. So, there are large number of climate variables for which the simulations are provided by the global climate models or the general circulation models. Now, as hydrologists, we pick up these simulations of the climate models and then relate it with the hydrologic variables. We will be interested in what is likely to happen to precipitation in a particular catchment, or what is likely to happen to stream flow at a particular in a particular river basin, what is likely to happen to evapotranspiration in the particular river basin and so on. These variables that the hydrologists are interested in are not well simulated by the climate models for various reasons. We need not worry about those things, but the variables that are really of interest to the hydrologists are not well simulated by the general circulation models. In addition, the general circulation models operate on large scales by their very nature, because they have to account for the entire globe. These are circulation patterns. So, which means you cannot afford to just look at one particular region in isolation. Everything is related, and therefore, the global climate models will generate the climate taking into account various grids across the globe. And because of that, because of the computational requirements, because of several other requirements, they essentially operate at large scales. What I mean by that is, the grid size of climate models is much larger compared to the size that is required for hydrologic impact assessment. So, because of these two major reasons, namely that the variables that are required in hydrologic applications are not well simulated by the climate models, and that the global climate models or the general circulation models provide the outputs essentially at large scales. Because of these two reasons, we adopt what is called as the downscaling. So, we downscale from the GCMs to the hydrologic scales. How we do this, we will study slightly, we will study in the present lecture. So, we pick up the simulations of provided by the general circulation models. We need the hydrologic variables at a local or regional scales, and this we obtain from downscaling of the GCM output. We use this to project into the future the hydrologic scenario. So, associated with the climate scenario, we provide a hydrologic scenario and then look at the risk associated with hydrologic extremes, let us say the droughts, the floods, and even the risk associated with operating a particular reservoir or water resource system in a particular manner, risk associated with hydropower being lower than a particular level, water supply being a particular level and so on. So, the risk associated with not only hydrologic extremes, but also with the various features of the water resource systems, and we develop risk based approaches and so on. So, this is a broad idea of what we do in hydrology in as much as climate change impacts are concerned. However, we will focus in the lecture essentially on downscaling techniques and a specific class of downscaling techniques called as the statistical downscaling techniques that use the transfer function approaches. When we do all of this analysis, the topics that we have covered in this particular course and some adaptation of those topics will come in handy in addressing the various levels of uncertainties. There are model uncertainties because we are relying on the global climate models or the general circulation models. There are a handful of such models. In fact, there may be as many as 25 such models for which the outputs are available across the globe, and there are many more coming. So, we have what is called as a GCM uncertainty, that is the general circulation model uncertainty. Depending on which model you choose, for the particular region that we are interested in, you may get different types of projections when you bring it down to the regional levels. There are various reasons for that. We will not, in this lecture, we will not worry about why the GCM uncertainty in fact happens. Then there is also a scenario uncertainty. As I said, scenarios are pictures of how the world is likely to evolve in future. Now, there is a enormous uncertainty associated with the scenarios, how the CO2 levels will be in the future, and because of which how the temperatures are likely to be in the future, and so on. Standing at this point in time, we are trying to project it into the future, and there are large number of uncertainties associated with scenarios. Then within the model itself, there will be some uncertainties because of the parameters and so on. The GCM uncertainty that I talked about are inter-model uncertainties. When you choose one GCM, it produces a certain amount, a certain type of projection, whereas another GCM produces another type of projection. That is inter-model uncertainty. But there are also intra-model uncertainties which arise because of the parameters that have been put into the GCM, the way the parameters are estimated, the way the boundary conditions are estimated, the way the initial conditions are estimated, and so on. So, that leads to intra-model uncertainty. Then as I said, from the climate models, we are bringing it down to hydrologic scales on hydrologic variables, and therefore, we are doing a particular type of downscaling. So, the downscaling itself produces certain uncertainty. So, there are large number of uncertainties when we are talking about climate change impacts on hydrology. The methods, the tools, the techniques that we have studied in this particular course will all come in handy when we are addressing these kind of uncertainties. So, in the probabilistic approach, I will just give a broad overview of what we do here, and in the particular application that I will be talking about in this lecture, that will deal with the drought index, or how the drought scenario is likely to evolve in a particular river basin. So, from the GCM we do a statistical downscaling using the principal component analysis and linear regression. We also add fuzzy clustering, but I will not cover that because we have not covered in the course the fuzzy clustering, but typically we have studied the regression using the principal components. So, I will just explain how these techniques are used in that. So, for doing this we need the GCM output, and the specific example that I will be covering, we will use the mean sea level pressure. So, mean sea level pressure is likely to affect the precipitation directly, and mean sea level pressure is well simulated by most of the GCMs, and therefore, we pick up mean sea level pressure as what is called as a predictor of the precipitation, which is called as a predictant. We are now developing a relationship between the predictant, which is the precipitation at a regional scale, with the predictor, which is the mean sea level pressure at several grid points, several GCM grid points. From this we get the subdivisional precipitation. In this particular case, we are talking about Orissa subdivisional precipitation, as I will show you presently. From this we get what is called as the standardized precipitation index of 12-month scale, and that is what we use as drought index, and we address the GCM and scenario uncertainty by fitting probabilistic probability distributions to the SPI 12, and then we address several levels of uncertainties. One is a data sample uncertainty itself. If your sample size is too small, size is reasonably small, and you are trying to fit a probability distribution to that, then the probability distribution itself will have uncertainty that we address through imprecise probabilities, and then finally, we provide the probability distributions for the drought index into the future. So, this is a broad overview. We will go into some of the details here. So, as I mentioned, the downscaling deals with bringing down from a larger scale like this. This is a GCM grid point until recently it used to be of the size 2.5 degree by 2.5 degree, that is 2.5 degree longitude, 2.5 degree latitude, which may be around 250 kilometers by 250 kilometers. That means, we are getting one output from the GCM for the scale of 250 kilometers by 250 kilometers. Whereas, on the hydrologic scale, if you want to run any hydrologic model, grid based hydrologic model, like for example, variable infiltration capacity model and so on, you will need these outputs at 15 kilometer by 15 kilometer, 12 kilometer by 12 kilometer and so on. So, these are the grid sizes required for hydrologic processes. In fact, depending on the process that we will be interested in, these need to be even smaller, of the order of 5 kilometer by 5 kilometer and so on. So, we must be able to bring down the GCM outputs to the hydrologic scales, and this we do by what is called as a downscaling. There are two major ways of doing downscaling. One is called as the dynamic downscaling, another is called as a statistical downscaling. The dynamic downscaling is beyond the purview of the hydrologists. In dynamic downscaling, they actually develop the regional climate models, taking into account the regional climate models take the boundary conditions from the global climate models, and therefore, for a given GCM you develop a regional climate model for a particular region. However, that is beyond the scope of hydrologists. So, we adopt what is called as a statistical downscaling. The statistical downscaling produces future scenarios based on statistical relationship between the climate variables. Let us say, in this particular case we are talking about mean sea level pressure. So, mean sea level pressure at a particular grid point, we may have mean sea level pressure here, and then we are interested in precipitation at a smaller scale. So, we develop statistical relationship between the mean sea level pressure at one or more grid points with the precipitation at a particular location. These statistical relationships can be as simple models as simple linear regression or multiple linear regression, to very complex models using the conditional random fields and so on, but essentially they use the concepts of probability and statistics. Once we develop this statistical relationship between based on the historical data, we hold this statistical relationship intact and then use it for future projections. So, the GCMs will provide the future projections. We use the same statistical relationship that is developed based on the historical data between, let us say, the MSLP, mean sea level pressure, and the precipitation. We hold this intact and then use the MSLP as projected by the GCM into the future, and then using the same statistical relationship we project the precipitation into the future. The main advantage of statistical downscaling is that it is computationally simple, and then any new area you can develop a new relationship for different GCMs, whereas for dynamic downscaling, for every GCM you have to develop a different regional climate model. Okay, we will just look at one application here. This region that is shown is the Orissa meteorological subdivision as provided by IMD. So, we have a rainfall series available for Orissa meteorological subdivision. This hatched area shows the Orissa meteorological subdivision and the location is here. Now, this region is sensitive to climate change because it is a, first of all, it is a coastal area. Then there are increase in hydrologic extremes that are evidenced in the past. It is subjected to both floods as well as droughts frequently in the past. Then we use the rainfall data available from 1950 to 2003. We have monthly data available. So, this time series is what is available to us. What we do is that we superpose the GCM grid points. This is a particular GCM, I will show you which GCM we are using and so on. So, you choose a GCM and then superpose on this area the GCM. If you have historical data at all these grid points on the climate variables that we have chosen as predictors, then we use the historical data to develop a relationship between the particular predictors at these various locations with the precipitation at this regional scale. So, we have the precipitation at this regional scale, which is called as a predictand. We want to predict that particular variable, and we have the climate forcings coming from what are called as the predictors. So, the predictor in this particular case is the mean sea level pressure. So, the mean sea level pressure values we may have at various grid points like this. In the absence of observed predictor values, data on the predictor variables, we use what are called as a reanalysis data. The reanalysis data essentially provide us the closest data to the historical point. They use a large number of data sets across the globe, and then they run idealized GCMs and then provide us with the data on all the climate variables. So, we will have the reanalysis data, and we also have the GCM produced data for the future. We use the reanalysis data or the historical data to develop relationship between the predictand, which is the rainfall here, and the predictors at various points, and then hold this statistical relationship sacrosanct, intact, and then look at the projections provided by the GCM, use the same statistical relationship and provide the projections of the precipitation. That is the principle of statistical downscaling. So, in this particular case, we use the GCM of CCSR Japan. This is a GCM, and then we use one of the scenarios just for demonstration. I will use this scenario now. It is called as a B2 scenario. It is from the third assessment report of IPCC, Intergovernmental Panel on Climate Change. We use the climate predictor as MSLP to begin with, mean sea level pressure, and we relate the mean sea level pressure with the precipitation at the Orissa meteorological subdivision, and the GCM output are provided up to 2100. So, you have certain output for calibration of your models, as well as you have the projections into the future. So, we use from 1950 to 2100. You look at this now, at each of these grid points you have one variable, mean sea level pressure, available at these locations, and then that mean sea level pressure is a time series, it is available in the form of time series. So, we use the monthly data of rainfall from 1950 to 2003. So, you have the time series of the rainfall, you have the time series of the mean sea level pressure at all of these locations. You can develop a relationship between the rainfall and these predictors. Because of the size of the problem, as you can see here, if you take 4 by 4, it will be 16, and then as your number of predictors increases, you will have larger number of variables involved in the regression, if you are using regression. Because of the size, as well as because of what we call as multicollinearity, which I discussed in the multiple linear regression topic, we do the principal component analysis to remove the multicollinearity and to reduce the size. So, we use the principal component analysis to identify how much of percentage of variance that is explained by the principal components. So, in this particular case, you can see first two explain almost about 95%. This is let us say 59 and this is 37. So, about 96% will be explained, but we can take up to the third principal component you choose for modeling purposes. All other principal components do not add to the explanation of variance significantly. So, we choose 3 principal components. Recall your topics that we covered in the multiple linear regression using the principal components. We use eigenvalues and eigenvectors, and then identify those particular principal components, initial few principal components which explain most of the variance in the data, and then choose these principal components for our further analysis. So, in this particular case we identify 3 principal components. Using these 3 principal components, we fit a relationship between the rainfall in a particular month. This is a monthly data we are talking about, rainfall in a particular month with the principal components. So, we write this simple expression. This is a regression equation. Rainfall in the month T is equal to some constant, and these are the k principal components, gamma k into P c k T. So, k is equal to 1 to k. Remember here the principal components will be different for different time periods. So, in this particular case we have chosen 3 principal components P c 1, P c 2, P c 3, all of which are different for different time periods, and these are the gamma values. So, we write the rain T as a simple regression form in a simple regression form as follows. When we do this for the training period, that means whatever data that we have used, let us say between 1950 and 2003, we fit the regression relationship and you get a R value of 0.789, which means predicted and the observed. The coefficient between the correlation between predicted and observed is 0.789, which is quite acceptable. In fact, we do several things to improve this. Let us say we do clustering, and then we do fuzzy clustering, and then we add a seasonality term, etc. All those details we will not worry about. We will say that we start with a correlation of 0.789 between the observed and the predicted. When we go into the future, now this equation is fit using the historical data. These PCs that are obtained are using the historical data. We use the same principal directions into the future and then use this equation for projected values of the climate variable, which is the mean sea level pressure in this particular case. When we fit the relationship, as I explained in our multiple linear regression, the residuals have to be normal, they have to follow normal distribution, and therefore, we check for the normality of residuals. What do I mean by residuals? That is the predicted minus the observed, that error series is called as a residual series. So, we fit the residual series. This is an unstandardized non-standardized residual. So, as they are obtained, we fit it and then see that it more or less fits a normal distribution. In fact, there are more rigorous tests that we carry out to examine whether the residuals in fact are normal and they are uncorrelated and so on, which I have explained in the time series analysis course. All of the time series analysis topics, all of those tests can be carried out. So, this is just to demonstrate that they in fact fit the normal distribution reasonably well. Then we also look at this is for the training of the model. That means, when we are building the model, we look at how well the observed mean and the predicted mean agree with each other. This we do for the wet season as well as the dry season. The wet season is our monsoon period, June, July, August, September, and the dry season is the remaining period. So, they fit very well, in fact 281.9, 283.3 and so on. So, mean as well as median we check for the model, and then we also check with the Nash-Sutcliffe coefficient, which is generally used in our hydrologic literature, which is given by this is the observed at time t this is predicted at time t, and this is the mean for the entire time period. So, this is how we calculate the Nash-Sutcliffe coefficient, and this is 0.83, which is very good. Once we are satisfied that the regression relationship that we have built is acceptable, then what we do is we go to this particular GCM and obtain the projections on the climate predictor. In this particular case, we have used only one predictor, which is the mean sea level pressure at those grid points. Look at this. So, we are looking at the mean sea level pressure provided by the GCM at these grid points. Now, these are available for download. If you go to the GCM site, you will get the simulations provided into the future for all the grid points. So, you can extract specifying your longitude as well as the latitude you specify, and then those grid points you will get the mean sea level pressures directly from the GCM website. You use those mean sea level pressures. In fact, there is a slight subtlety here. As I mentioned, we may use reanalysis data, and the reanalysis data which is given by, typically we use the NCEP and NCAR reanalysis data. And what happens is, in most cases, let us say this is the GCM grid point, your NCEP grid point may be somewhere here. So, this is NCEP grid point and this is a GCM grid point. Let us say we are using a particular GCM and the GCM is here, grid point is here, whereas your reanalysis data is here. And we would have developed the reanalysis, we would have developed the regression relationship with the reanalysis data. And therefore, when we use the projections, these projected variables or the projected simulations must be brought to this grid point, that is the NCEP grid point. So, we need to interpolate the values that are provided by the GCM at particular locations to the NCEP grid points, and this we do typically by what is called as a spherical interpolation. So, we use spherical interpolation for interpolating between GCM grid points and the NCEP grid points. This is just a broad idea, but there are lots of improvements that are available, that are possible in what I just told, and spherical interpolation is readily doable using MATLAB programs. So, in MATLAB you have a routine to carry out spherical interpolation. You can use that toolbox, and then in fact, there is a function for spherical interpolation. You can use that and then do the spherical interpolation. But what is important to understand here is that you are developing these kind of relationships with respect to the reanalysis data, and the reanalysis grid points, for example, NCEP grid point, NCEP is National Center for Environmental Prediction USA, those grid points and the GCM grid points may not tally, and therefore, you have to do an interpolation. So, when we do this using the particular scenario that we are interested in, as I said, we are using B2 scenario here, and with one particular model, this is a CCSR NIES model, this is a Japanese model. We use this for the particular scenario and then project it into the future. Up to 2003 or something, we use it for building the model, and then the remaining part we use it for projecting, and this is the long term mean. So, you may see certain trends that the precipitation mean may be falling up to certain point and then rising beyond a certain point in time and so on. So, we see certain patterns as we project it into the future. This is for the wet scenario, this is for the dry scenario. Dry scenario may be falling down like this. However, the point that is important and the point where the uncertainties start arising is as you change this model and as you change this scenario, you will get different pictures altogether. So, instead of this model, if you use another model, you get a different picture altogether. Instead of this scenario, you choose another scenario, let us say instead of B 2, you may choose A 1, then you may get a different scenario altogether. And that is what causes uncertainty, because you are interested in obtaining the hydrologic scenario. For example, you are interested in seeing how the precipitation is likely to change in future. And this uncertainty needs to be addressed if we are using these kind of scenarios for our planning purposes, which is what is the final goal. So, we convert this precipitation time series into what is called as a drought index. So, we use the several drought indices are available. I will not go into details of those. We will use what is called as a standardized precipitation index SPI, which is a indicator of meteorologic drought. It just requires the precipitation values. Using the precipitation values, you convert that into a standardized precipitation index. There are other indices like Palmer drought severity index, Bahme-Mooley index, and then effective drought index and so on. But the SPI is the simplest one that we use for assessing meteorologic drought. We convert the precipitation series into the SPI as follows. We fit a probability distribution to the precipitation series. So, this is the annual rainfall here, and then we fit a probability distribution CDF using our Weibull method or whatever. So, these are Weibulls plotting position, and typically annual rainfall, as I have mentioned when I covered the probability distributions, you may fit a gamma distribution. So, the gamma distribution in this particular case fits reasonably good. Then we convert this distribution to a standard normal distribution. So, any point here you just transfer it into standard normal distribution, and that gives you the standardized precipitation value. What I mean by that is, let us say that you start with a particular value here, go up, reach the curve and come horizontally, reach this point, and this value will be the SPI 12. That is how you convert the precipitation time series into the SPI 12 values associated with various values of this. So, you get a SPI 12 on the x axis here associated with the standardized normal CDF, starting with the CDF that you have fit for the annual rainfall. So, you get various values of the SPI 12. Now, this SPI 12, depending on the value that you get here, these will indicate the drought category. So, 0 to minus 0.99, it indicates a normal situation, and so on, mild to moderate drought, then severe drought, extreme drought, etc. This is based on the SPI, that is standardized precipitation index, and the reference is available here, Mackey et al. 1993. We use, I just explained how we obtain the SPI 12 computation. So, we do this both for the observed annual rainfall as well as for the GCM output. So, with the GCM output, we have done the statistical downscaling using the regression relationship, and then we have obtained into the future, we have obtained the time series of the precipitation, and then we compute the SPI 12 for the future. And then look at how the SPI 12 is likely to evolve into future when I use several GCMs, different GCMs for different scenarios. So, these are the different GCMs that we use for different scenarios. Remember what I talked about just now was precipitation projection. So, this gives the precipitation projection for a given GCM and for a given scenario. This precipitation projection will then be converted into a SPI projection, standardized precipitation index, to indicate how the drought picture is likely to evolve in future, and that we do for several GCM scenario combinations. So, each of them will show one GCM scenario combination. For example, this curve may indicate AOM NASA for a 089 scenario, then AGCM CCSR for A1 scenario, CGCM to IS92A scenario. So, each curve represents the projection provided by a particular GCM for a given scenario. As you can see here, there is a large amount of uncertainty associated with these projections, even when you are looking at time periods of 2040s. So, there is a large spread that is being seen here, but this band or this spread starts increasing as you go into the future. 2040 to 2060 the band is much higher, as you go into 2080s it is much higher, and so on. So, the uncertainty propagates into the future, and it is important for us to quantify the uncertainty when we want to use these projections for our decisions, as well as develop methodologies and tools to see whether we can reduce the band of uncertainty, because with this kind of uncertainties it is very difficult for us to use this information into any decision making mechanisms. One way of doing this is, let me show the same thing we are using the box plots. So, when we have these kind of projections, we generally provide, as I told in the last class, we provide the box plots. So, in 2020s we get a certain type of uncertainty, certain type of range, certain type of mean, median, and so on. 2040s we show something, 2060s we show. So, typically the box plots are used to show the uncertainties as you progress in time, in the case of projections using the climate change. All right, now we look at this. So, at various points here 2020s you have a certain ensemble of time series. So, this is essentially an ensemble of time series. So, at 2020s you have certain spread and certain realizations, and 2040s you have certain different spread here and so on. If you assume that all these models and all the scenarios are equiprobable, that means in the future they all have the equal likelihood of providing the right projection. That means, this projection is as likely to occur as this projection because of our lack of knowledge. We address the first level of uncertainty, assuming that all these projections are equiprobable in future, and then fit probability distributions for various locations. So, you look at 2020s, you fit a probability distribution based on the sample that is available at 2020. 2040, you fit another probability distribution based on the sample that is available at 2040, and so on. So, we provide the probability distributions of the SPI 12 as the time progresses. This may be 2020, this may be 2040, this may be 2060, and so on. We will then examine how the probability distributions are likely to change in future. The probability distribution has absorbed or has used all the information that is available through these projections. So, at any particular given time it uses the several time series values that are possible 2040s to 2060s. Let us say this particular time frame, you will use all the time series and then develop the models. So, these are typically done for time windows, not at a particular time 2020, it may represent 2020 to 2040, similarly 2040 to 2060. So, you use the ensemble analysis and develop probability distributions at those time windows. The way we do is simply assume that every time window it follows a normal distribution, and then get the parameters associated with that, associated with the normal distribution. So, this way you are trying to address the uncertainty, first level of uncertainty. You simply say that all model scenario combinations are equally possible. What I mean by that is the projections provided by any model scenario combination is as likely to be possible as the projections provided by any other model scenario combination. And then you look at different time windows 2020, 2040, 2040, 2060 etcetera. You have an ensemble of time series during that particular time period. Assume that this follows normal distribution. That means, when you fit a distribution to that particular ensemble, it follows a normal distribution, and then you estimate the parameters of that and then provide how the droughts are likely to evolve in future. The other one will be you use a kernel density estimation, which I will explain presently, and then come out with the actual probability distributions using the kernel density function estimates. So, when you use the normal probability distribution, you get such picture in this particular case. The near normal condition, the probabilities will be like this, the mild drought, the probabilities will be like this, extreme drought, the probabilities are like this, and so on. So, these are obtained from assumption of normal distribution to the various time periods. So, this is 2000 to 2010, 2040 to 50, 2090 to 2100 and so on. So, like this different time periods you use and estimate the probabilities associated with the mild drought, extreme droughts, severe drought and so on. In the kernel density estimation, what we do is that we fit the probability density. This is the kernel density estimator of probability density. This is the number of observations. In our case, it will be the number of simulations that are possible, and this is called as a smoothing parameter, and you have the kernel functions here. Now, this smoothing parameter, which is called as a bandwidth, it is important to assume a certain form of the bandwidth, and that in this particular case we assume that the kernel is Gaussian, and therefore, we get this kind of bandwidth here. We will not go too much into detail, you just distinguish this between what we get with the normal density as well as kernel density estimator. The kernel density estimator again can be obtained directly from a MATLAB subroutine. So, when you do the kernel density estimator, you get near normal condition like this, and then the severe drought, extreme drought probabilities are obtained like this. So, essentially then what we are doing is that we are using the downscaling technique to project into the future. In this particular case study, I have talked about projection of the precipitation at a meteorological subdivision and specifically the Orissa subdivision. We project the precipitation into the future using several GCM scenario combinations, convert the precipitation into a drought index, and in this particular case we have used SPI 12, the standardized precipitation index, which is computed based on the monthly data, and that is why the 12 months data comes into picture. Because you get a spread, because you get an uncertainty band at various time windows 2020 to 2040, 2040 to 2060 etcetera, you fit probability distributions of the SPI 12 for those windows. The first level of assumption that you make is that you simply assume that at each of these time windows it follows normal distribution, and then obtain the parameters of the normal distribution, namely the mean and the standard deviation for those different time windows, and then assess what are the probabilities of various levels of drought, extreme drought, normal situation and moderate drought and so on, based on the ranges that are available for the SPI 12. Next, you use a kernel density estimator, which can also be done using the MATLAB program, and then you again assess probabilities of various levels of droughts. So, this is how you address the uncertainties arising out of the GCM and the scenarios. As I mentioned, our primary hypothesis here is that the projection provided by any GCM is as likely to occur as projection any GCM scenario combination is as likely to happen as projection provided by any other GCM scenario combination, which means they were saying that all these time series are all these projected time series are equally likely to occur in future. Based on that, we address the uncertainty. There are other questions to be asked in the uncertainty. Before I close, I will just explain those things and then we close the lecture. It is possible that these are all not likely to these are not equally likely. Then what we do? We start assigning weights to the projections provided by a certain GCM scenario combination. How do we assign the weights? We assign the weights based on how well this GCM scenario combination has performed for the particular region in the immediate past, let us say between 1990 and 2005 or 2010, 1990 and 2010, how the particular GCM scenario combination is able to reproduce exactly what has happened to the precipitation in that Orissa subdivision between 1990 and 2010. Based on how well it has been able to reproduce, we assign weights. So, different GCM scenario combinations will have different weights and we provide what are called as a weighted probability distributions. Then we also address the question of the imprecision in the probability assessment because of the small sample. As I said, even if you get all the models and all the scenarios, perhaps you may have about 100 samples, 100 time series. So, at any particular location when you are looking at the probability distribution for a particular month, you have maximum of 100 values. So, this is a small sample that we are talking about. In fact, even 100 you will not have, as I showed in the particular case, you may have about 20, 25 values and 20, 25 values you are trying to fit a probability distribution. Therefore, the probability distribution itself will not be precise. Then we move on to what are called as the imprecise probabilities. So, we develop imprecise probability distributions and then provide bounds of the droughts. That is, what is the probability bound for extreme drought, what is the probability bound for normal conditions and so on. Now, these informations, this type of information will be extremely useful in planning for the future. Let us say that you want to plan for agricultural use of water into the future. So, you must know what levels of probabilities exist for drought in various regions of the country, and this kind of information will be useful for that. So, today's was a special lecture on using the stochastic hydrology techniques that we have learned in the particular course for the most timely problem of climate change impact assessment. And as I mentioned in the class in this particular lecture, the climate change impacts, the assessment of climate change impacts is burdened with a large amount of uncertainty arising out of the GCM uncertainty, the general circulation model uncertainty, the scenario uncertainty, the downscaling uncertainty and the intra-model uncertainties themselves, that is the model uncertainty. So, it is important for us to use the techniques and the tools that we have learnt in the course to address all these kinds of uncertainties, and I have provided a simple example of using the GCM outputs to project Orissa rainfall into the future and then addressing uncertainties by providing probability distributions for different time windows, and these probability distributions will be useful for planning purposes. Using the probability distributions, you can plan for agricultural activities, you can plan for you can convert them into stream flow scenarios and so on, and then plan for reservoir operation. So, developing adaptive responses will require these kind of projections. So, the next lecture, which is the lecture number 40, will be the last lecture of the course, where I will summarize whatever we have taught, we have discussed during all these 39 lectures. Thank you for your attention.